Hello everyone. In this lecture we will be discussing the concept of Wasserstein GANs, which we in short call as WGAN also. So before discussing the concept of Wasserstein GAN, we have to understand some basic concepts that lie behind understanding this concept, that is the WGAN. In order to understand this completely, what we will do is we will first of all understand the drawbacks of KL divergence. This KL divergence is basically discussed in greater details in my video lecture DL_20. So if you want to understand how we are deriving the KL divergence for two different probability density functions, I suggest you to look at this lecture first before coming here. And then after understanding that KL divergence from here, then our main focus in this lecture will be to understand what drawbacks this KL divergence has that resulted in the formulation of JS divergence, which is also called as Janssen-Shannon divergence. Janssen-Shannon divergence. So this type of divergence is basically used in generative adversarial networks, which you must have seen if you have watched my earlier lectures on GAN. In that we had this JS divergence coming in the loss function of GANs. So definitely GANs have an upper advantage over the variational autoencoders, which basically use KL divergence as one of the terms in its loss function. So since GAN has an upper hand over variational autoencoders, which in turn is because the JS divergence has an upper hand over KL divergence. That is why GAN performs better as compared to variational autoencoders. So we will see how come JS divergence is better than KL divergence. And then the concept of Wasserstein distance comes up. This distance is basically used as one of the metric in loss function of WGANs. And this distance metric is much better than JS and KL. So whatever disadvantage KL and JS divergence has, Wasserstein distance actually overcomes that disadvantage and hence results in improved performance of WGANs. So you can see the roadmap, and the roadmap is that the researchers initially started with variational autoencoders. Then some of the researchers found that there is a problem with KL divergence, so they moved into generative adversarial networks that uses Janssen-Shannon divergence. And later on, some researchers have found that Janssen-Shannon divergence also has some disadvantage, so they moved to Wasserstein distance and formulated WGANs. So you can see the progress, and this is what is called as a research progress. So if you don't know this path, that how it formulated from variational autoencoders to GAN to WGAN, then it's highly impossible for you to further conduct the research and improve WGAN to next level. So in order to, and my aim is to make you understand this research progress so that you are ready to further progress from WGAN and create more variants of WGAN which have improved high performance as compared to this existing WGAN. So without wasting our time further, let's see what disadvantages KL divergence has and how we are overcoming it using JS divergence. So now our main focus is first on KL divergence. So as pointed out earlier, this is discussed in greater details in DL_20. So if you want to see what this KL divergence is and how to calculate it for two different probability density functions, then I will suggest you to watch this lecture first before coming here. And further, I have a complete lecture series from DL_19 to DL_24, which has a complete discussion about variational autoencoders, which uses this KL divergence as one of its loss function. So I suggest you to watch these lectures also before jumping on to this series of WGAN. So now what I have not discussed in that lecture, I will discuss here. And that thing is, this KL divergence has two different forms. One is forward KL and the other one is reverse KL. So if you have two probability density functions, let us say P and Q, and here this P is the unknown probability density function which you want to approximate through Q, which is basically a normal distribution in some sense, which we take as normal distribution for simplicity. So this Q we know and this P is unknown, and we are trying to approximate P using Q. So in forward KL, what happens is we have this term which is P, the distance between P and Q, as summation Px log of Px by Qx. So this is the forward KL. How about the reverse KL? Reverse KL is nothing but it is Q with respect to P, and that is given as Q of x log Qx over Px. How to measure this I have discussed in greater detail in DL_20. I suggest you to watch that first. So this is basically reverse KL and this is forward KL. And what is the target of variational autoencoders? If you have watched my series, then you will immediately correlate with this what I am writing over here. The target of variational autoencoder is to minimize the KL divergence between Q and P. And this P is unknown and this Q is basically parameterized by phi. And we are actually minimizing the KL divergence, and we are finding that optimal phi that minimizes this argument. So that is the basic concept of variational autoencoders. So the question is, why we are using this form only? Why not the other way around? That is, why not minimization of KL P with respect to this? So this is the question. Why we are not using this? So let's see what information we can achieve from these two divergences. So let's discuss the forward KL first. The forward KL is represented as minimization of phi, minimization of KL divergence of P with respect to Q parameterized by phi, where phi is actually the parameters of the neural network that we are optimizing in order to minimize this KL divergence between P and Q. So now if we incorporate the definition of KL divergence, what that will be? It is minimize with respect to phi the KL divergence, that is Px log Px over Qx. So this we are taking from the definition of KL divergence. So what you can observe here, at what point the log will have very high value? The point where Px has some value, it has some value, whereas Qx is 0. So at that point what will happen? At that point the log will be having very high value, right or not? So let us say I have a unknown probability probability distribution which is unknown to us, and it is given as this. This is my unknown probability distribution P, and our known probability distribution is given as this. So this is our Q. This is our known probability distribution. And what we are trying to achieve? We are trying to do what? We are trying to minimize the distance between this Q and this P using KL divergence. So what will happen? So in this situation, in this type of probability distribution, what will happen is that it can be possible that our known probability distribution Q will form like this distribution in order to approximate P. But this situation has a problem. What is the problem? The problem is at this location. What problem it has at this location? The problem is that here P has a value, that is probability density function P has a value. You can see the values over here, but Q is 0. So as a result of which what will happen? As a result of which log will be having very high value because it is dividing by 0. So it will be having a very high value. But what is our function here? Our function is trying to minimize this argument, right? The KL divergence. So as a result of which the optimization framework will avoid this situation, that is this situation that I am discussing over here, that is the zero avoiding situation. This is basically called as a zero avoiding situation, because here qx is 0. So what our optimization is doing is it is trying to minimize this argument which is getting infinity at this point. So it is trying to minimize this argument. So in order to minimize this argument, what will happen is the new function will form like this. This is our new qx. So this will be our new qx. And here the problem is removed. Why the problem is removed? As you can see over this point. That is, you can see that both of them, the blue curve and the one which you are approximating it using q, are 0 over here. So when these two are 0 over here, then it is actually 0 log 0 by 0. So it's actually effectively 0. So this distribution is favorable for this optimization framework, and it is also sometimes called as mean seeking or zero avoiding situation. Why it is called as that? Zero avoiding, I told you, because this situation where it is coming as 0, you can see as I was discussing, this situation which is 0 over here is avoided by moving the distribution from this to this. And it's called as mean seeking because it is centering at the mean of these two bimodal distributions. So it is centering in the mean position of that. That's why it is sometimes also called as mean seeking. So forward KL is basically mean seeking or zero avoiding, and it tries to stretch the distribution Q. As you can see that the earlier distribution of Q was this, and it stretched the Q distribution to this part. So it's basically stretching the distribution to cover the entire bimodal distribution P. So this is important. So this is basically the concept of forward KL divergence. So now we will discuss the concept of reverse KL. What is reverse KL? Reverse KL is nothing but minimization of KL divergence between Q of phi with respect to unknown distribution P. So this is our reverse KL, and we are optimizing this, we are minimizing this KL divergence by tuning the phi parameters, right? So this is our reverse KL. So now consider the situation where the unknown distribution P is again bimodal, and it's represented like this. Okay, so this is our unknown distribution which is P, and let us assume that our Q phi is basically this. So if this is the situation, this is basically our Q phi, that is the probability distribution with which we are approximating P. So if this is the situation, let's see the concept mathematically first. So what we are doing is we are minimizing the KL divergence, which is basically now Q of phi log of Q of phi over P of x. So this is what we are doing, right? So again with the same argument, and if Q of phi x is something, it has some value, but if P of x is 0 at that point, what will happen? At that point log will again blow up because it is dividing by 0. So it will again blow up. So where is this situation happening in this curve? It is happening in the areas over here. You can see that our P is 0 over this point, but Q has some value still there. So as a result of which the KL divergence in this region is very high. Here it is infinity. The KL divergence is infinity in this region, and similarly here also. And what is our target? Our target is to minimize the KL divergence, which is right now coming as infinity at these locations. So in order to minimize the argument, that is reducing the value from infinity to some minimum value, what will happen is it will force the Q phi probability distribution function to become like this. That is, it will become like this. I'll redraw this again. So this is our probability distribution P. Then our Q will become like this. That is, it will be having 0 here, and then it will have 0 here also. Why like that? Because here it has to be 0, so that it will be 0 log 0 by 0, which is effectively 0, and the KL divergence will not be infinity here anymore. It is minimum, reaching it at as 0 by forcing this purple curve to become 0 here, which was not earlier the case, and it was coming because we are doing minimization operation on this KL divergence. And second thing is, by contracting this distribution, that is the purple one, to lie within this single mode only. So you can see that this whole distribution, which was earlier covering the two modes of P together, that is first mode and the second mode, it is covering the whole probability distribution function, is now covering only the single mode of this P, and this is 0 over here. This is allowed. Why? Because at this point what happens is, it is actually Q of x which is 0 and Px is having some value. So it is 0 log 0 divided by some value, which is approximately 0. So this region is satisfied now. And one may say that why P is not forming in a way as that of P, that is like this. Why it is not forming like this? It is not forming like this because we have assumed it to be a normal distribution, not the bimodal distribution. That's why it is like this only. So what's the operation of reverse KL? Reverse KL is basically shrinking. It's basically shrinking the probability distribution which was earlier lying in both the modes to a single mode. And it is also sometimes called as mode seeking behavior. Why we call it as a mode seeking behavior? As you can see that it is seeking this single mode. Instead of having both the modes, it is seeking one single mode. That's why it's called as mode seeking behavior also. So this is basically the concept of reverse KL. So this is basically quite graphically I have explained you the operations of both forward and reverse KL. In the next slide we will discuss the mathematical details and see on what reasons we are not using forward KL for our purpose of variational autoencoders, and why we are using only reverse KL in variational autoencoders. So you can see that in reverse KL, it's basically underestimating the probability distribution P. By underestimating means the probability distribution Q is underestimating the probability distribution P because it is estimating only one of the modes, which is over here. But it is somehow estimating it in much better way as compared to that in case of forward KL, where it is overestimating the probability distribution P over these areas, It is overestimating over here. And sometimes it is more worse, because this is I have shown you in a more decent way, but it happens that sometimes it can estimate something like this. This I have shown you for my illustration purpose, but it is quite possible that it can happen to estimate Q like this, where the overestimation is this. This is basically the overestimation part. So considering this, underestimation is much better as compared to that of overestimation. Hence we use reverse KL in variational autoencoders. So now what we will discuss next is what inherent problem is there in KL divergence, which is basically in both forward as well as in the reverse situation. That is an inherent problem in it. So let's discuss that inherent problem and what is the possible solution of that. So let's discuss one of the basic problems of KL divergence, and this basic problem exhibits by both the forward as well as the reverse KL. It is not that this problem is only with forward KL, it is with both forward as well as reverse. So let's discuss one situation where KL divergence fails to get evaluated, and let's see how we can overcome this failure by using some other measure. So let's move to the next slide. So let's consider this situation where we have two probability distribution functions given as this. So we have one probability distribution function given as this, where it is 1 at 0th location, and the other probability distribution function, and this is, let us say, P, and another probability distribution function which is 1 at, let us say, 0.5, and this is distribution Q. A detailed discussion about KL divergence for an arbitrary probability distribution function is already discussed in my earlier lecture, that is DL_20. So if you want to see how we derive it for an arbitrary probability distribution function, a discrete probability distribution function, you can go and check out there. But here I am considering an exceptional case where KL divergence fails to evaluate. So this is basically an exceptional case where it fails to evaluate, whether it's forward or reverse in any of the situations. So if we want to calculate the forward KL divergence, then what will that be? It is probability of x log of px over qx, right? So when you will evaluate this at x is equal to 0, so what will that be? Considering this probability distribution function, px is 1 at small x is equal to, this is basically small x. So let's expand this first. So it's basically probability of x, it's basically probability of x at 0 times log of probability of x at 0 divided by probability of q at x equal to 0. So once you evaluate this, what will be the values? Here this is 1, here this is 1, but here what will the value of q be? The value of q at 0 is 0. So what this evaluates to? This evaluates to infinity. And how about the other way around? That is KL q given p, then it will be also infinity. As you can check, it will be q at x equal to 0, q at x is equal to 0.5, then log of q at x is equal to 0.5 divided by p at x is equal to 0.5. So this value is 1, this value is 1, this is 0 because there is no value at 0.5 over here. So this also evaluates to infinity. So what observation you can see from here? The observation that you can see is that if the two probability distribution functions have no overlap, then there is a chance that your KL divergence will blow up, as you can see over here. So this is basically one probability distribution and there is no overlap of this with this probability distribution. So there is a high chance that the KL divergence when evaluated will give you infinity. In all our earlier cases, we have assumed that the probability distribution functions are overlapping. This in terms of continuous setting can be seen like this, that if you have a bimodal P over here, then Q is somewhere far away from this bimodal P, and that is, it is over here. So as you can see that at this situation the KL divergence will turn out to be infinity. However, if Q was overlapping with this, then this would not be the case, which we have discussed till now. However, if Q overlaps with P, then this situation of KL equal to infinity will not occur. But normally in practical situations, this Q is far away from P. So that's why the chance of getting KL equal to infinity will always be there. So in order to avoid this situation, that is this of infinity value, another measure is taken into account, and that measure is known as Jensen-Shannon divergence. What is that Jensen-Shannon divergence? It is, in short, we call it as JSD. It is basically between two probability distributions P and Q, that is equal to half KL divergence between P and M plus KL divergence between Q and M, and where M is basically the average of these two distributions. So in this situation, if we consider our PDFs which we have just shown over here, then if we want to write the JSD for this situation, then what it will be? It will be P of x equal to 0 log P of x is equal to 0 divided by P of x is equal to 0 plus Q of x is equal to 0 divided by 2 plus, and this is basically for this and for this, so it will be Q of x is equal to 0.5 log Q of x is equal to 0.5 divided by P of x is equal to 0.5 plus Q of x is equal to 0.5 Q at x is equal to 0.5 divided by 2. So once you substitute these values, what will you get? You will get half, this is 1 log 1 divided by, at this point this is 0, so it will be 1 by 2 plus Q at x is equal to 0.5 is again 1 log 1 divided by P at x is equal to 0.5 is 0, but Q at x is equal to 0.5 is 1, so it's half. So this is basically log 2. Instead of getting a value of infinity in case of KL divergence, you are getting a log 2 value in case of Jensen-Shannon divergence. This is very important result. Why it is important? The reason for this being important is, normally when you approximate any distribution, that is if you are approximating P with the known distribution Q, then it is very highly unlikely that these distributions will overlap with each other. So in the situation when they are not overlapping with each other, using KL divergence as the means of optimizing the results, as in case of variational autoencoders, will not lead to the proper results. Whereas if the cost function has Jensen-Shannon divergence as one of its terms, then this situation can be easily handled where P and Q are far away from each other and there is no overlap. So that is the point where generative adversarial networks have advantages as compared to that of variational autoencoders. The advantage is that in case of generative adversarial networks, the loss function of the generator for optimal discriminator has Jensen-Shannon divergence as one of its terms. So this helps us in targeting the situation where P and Q are not overlapping but they are far away distributions. So that's why GAN has an upper hand over variational autoencoders. So let's discuss this point which I have pointed out to you in more details in the next slide. So you may recall in case of generative adversarial networks, what we were doing, we were trying to approximate this distribution of MNIST fashion data set, which is D, using the distribution that is output by generator G over here. So this distribution which is generated by generator G is totally different from the distribution D over here. So it is highly unlikely that there is an overlap in between these two distributions. So measuring a KL divergence for optimizing the loss function of generator in case of this case will highly result into the KL divergence giving up a value of infinity. That's why JSD divergence, which is appearing in one of the loss functions of the generator when we put the optimal discriminator value of D star, that's why the JSD term appears in the loss function of generator, which helps us in dealing with this situation where these two distributions are totally different from each other. We will discuss more about this in our next lecture, but for now being, you can safely assume that that GAN are producing superior results because of the distance metric that it is using is JSD in comparison to that of KL, which is used by variational autoencoders. So this is important. Later we will see that JSD is also not a suitable metric to be used. It also has some drawbacks which we will analyze in our next lecture, but for now, for this lecture, you can safely assume that JST is much better than that of KL divergence. So in the next lecture, we will discuss another type of distance, which is Wasserstein distance, and we will see what advantages this has as compared to that of JSD and KL divergence. So this is another type of distance that is introduced, and our Wasserstein GAN are based on this metric. We will discuss the details of this distance in our next lecture. Thanks for watching my lecture. See you next time.